Hi folks. Today I have a lesson for you on initial rates and how to determine a rate law for a reaction using experimental data. So for this example, we can see uh, the information that is provided. For this reaction, they have given us a balanced chemical equation where we have 2NO2 gas plus 3O2, O3, forming N2O5 plus O2, and they're asking us for the rate law. Now, the generic rate law would be equal to rate is equal to K, concentration of the reactants, which is NO2, to the power of X. We don't know what the X is, which is the order for NO2, and square bracket O3, ozone, to the power of Y, which is the order for the ozone, O3. Okay, this is the generic rate. But when you're looking for the rate law, we also have to find the value of K, the value of X, and the value of Y, and write for the rate law. Okay, so to find the X and the Y, okay, there is a long way of doing this and the short way of doing this, right? The long way is you have to look at the experimental values given to you, and you have to take two of them, divide one by the other. And again, we do this strategically. It's not just taking any value and dividing by the other. It's taking two values strategically and dividing one over the other, or dividing two rate laws one over the other. And I'll explain what I mean over here. So if you see the values here for experiment 1 and experiment 2, okay, and what we see is NO2 is the same concentrations for both of them. Both of them are 0.100 moles per liter. Okay, so the concentration of NO2 is not changing, but what we can see on the right hand side is the concentration of O3 is changing, right? So in other words, what can we do with this data is we can identify the change, the impact of the change of the O3 has on the rate of the reaction. Does it make the reaction faster? And by what factor, right? So usually X and Y are whole numbers, and so we need to find out by what factor does it affect the rate, okay? So the NO2 concentrations have not changed, but the ozone concentrations have changed. All right, so how are we going to do it in the long way? Let's write down the rate. And I'm going to do rate 1 divided by rate 2. And that will give me a whole number, and that's why I'm picking rate 1 over rate 2. So rate 1 is equal to K, concentration of NO2, which is 0.100 to the power of X, square bracket 0.200 to the power of Y. All right, divided by the rate 2, which is again K, square bracket 0.100 to the power of X times 0.100 to the power of Y. Now when we solve this, we can plug in the rate values as well, and let me plug in the rate values here. Rate 1 was 1300, and rate 2 we have is 650. Okay, now once we have this information, now what we can do is we can start canceling things out. So I'm going to switch pens here to try to cancel things out, which are the same on the top and the bottom. The K and the K is identical. It's the same K because the reactions are taking place with the same temperature. So the K values were the same, and so they got cancelled out. The 0.100 times 10 to the power of X is also cancelled out because that's on the top and the bottom. And what we have left over is 1300 over 650 is equal to the 0.200 to the power of Y divided by 0.100 to the power of Y. Okay, so 1300 over 650, that is a value of 2, is equal to Now we over here have a square bracket. We are going to take this whole value to the power of y, common, 0.200 over 0.100, which is essentially saying 2 to the power of y. So 2 to the power of y is equal to 2. What is the value of y? Y over here is equal to 1. Okay, so we have just identified what the value of y is. This is 1. Okay, and so we picked the experiment number 1 and 2 strategically so that the 0.100 will cancel out from the top and the bottom, and the data will tell us the effect of ozone, the change in concentration of the ozone. Okay, we have to do the same kind of idea for the other reaction so that we can figure out the impact of the NO2. So in this case, you have to look at the data where the NO2 is changing. Okay, so let's try this out. So in the first part of the video, we were able to find out the value of y. The value of y was equal to 1. In the second experiment, now we want to figure out the value of x. Now to figure out the value of x, we have to pick two experimental data points or two experimental trials where the NO2 value was changing or different. In this case, I'm going to pick experiment number 1 and experiment number 3. So I'm going to now try the same equation. So I'm going to do rate 3 over rate 1. Okay, and so let's do that for the two. So rate 3 will be equal to 5200 is equal to k square bracket of 0.200 to the power of x, where we don't know what the value of x is, square bracket 0.400 to the power of y, which is 1. We already know that value, over the value of rate 1 is 1300 is equal to k square bracket value of NO2 is 0.100 to the power of x, and value of O3 is 0.200 to the power of 1. Now we can divide the values and see what we have to just simplify the equation. Now we have the k on the top and the bottom that can be cancelled out, and now we have 5200. So I'm going to use a calculator. 5200 divided by 1300, which is equal to a clean 4, is equal to I have 0.200 divided by 0.100 to the power of x, and 0.400 divided by 0.200 to the power of 1. That gives me, if I simplify that, 4 is equal to 0.200 divided by 0.100 is equal to 2 to the power of x, and the 0.400 divided by 0.200 is equal to 2 to the power of 1, which is equal to 2. So simplifying it further, we can say 2 is equal to 2 to the power of x, and therefore x is also equal to 1. So now we have found the value of x and y. So in the rate law, rate is equal to k square bracket of NO2 to the power of 1 and O3 also to the power of 1. But we are not done yet. We have found the value of x, we have found the value of y, but we have still not yet found the value of k. Now for finding the value of k, we usually use experimental data point 1. So experiment 1, we will use the values of experiment 1 to find the value of k. So K is equal to, just rearranging the equation, is equal to rate over concentration of NO2 over concentration O3, and now plugging in the values. Rate for number 1 is 1300 over 0.100 and 0.200, and now it's just a matter of using the calculator, and that gives us 1300 divided by bracket 0.100 times 0.200. So that is a value of 65,000 for the value of K. Right? Now, one more thing to keep in mind is the units. The K's units will change depending on the order of the reaction. So, when we are actually solving for the value of K, it is recommended to keep the units intact in your calculation. So, I'm going to redo this calculation. I'm going to get rid of this because this will not help me figure out the units. I need to keep the units intact. So rate, again, I'm going to put it back in as 1300 moles and I can keep molarity, that's fine because that is going to cancel out. Big M over S over you have concentration, which is 0.100 molar and 0.200 molar, right? And so what this is going to do is we are going to get the same value. The magnitude is the same, 65,000, but now we have to figure out the units. Now the M and the M will cancel out. S is in the denominator and the M is also in the denominator. So it would be M to the power of -1, S to the power of -1. So the units for K will be per mole per second. And now the time to put the rate law all together. So rate law for this reaction is equal to 65,000 per mole per second, concentration of NO2 to the power of 1, concentration of O3 to the power of 1. And that is my entire rate law. So that is my final answer. That's my final rate law. Rate is equal to 65,000 per mole per second times the concentration of NO2 to the power of 1 and concentration of ozone O3 to the power of 1. I hope you enjoyed this lesson and you are able to understand the value of the exponents in the rate law and the value of K and how to calculate the value of X, Y, and K in a rate law.